Okay, so today we're going to continue with direct proof and counterexample. A little section on writing advice. We're talking about writing a proof. All right. Give some steps here on how to write proofs. It says the following rules of style have become fairly standard for writing the final versions of proofs. Number one, copy the statement. Of the theorem to be proved, of what is to be proved. This makes the theorem statement available for reference to anyone reading the proof. Two, clearly mark the beginning of your proof. You usually use this by using the word proof, separating the general discussion about the theorem from its actual proof. Make your number three. Make the proof self-contained. So if you're going to be using variables, define the variables within the proof. You begin proofs by introducing the initial variables and stating what kind of objects they are. The first sentence of your proof would be something like, suppose m and n are any even integers, or something similar. This is similar to declaring variables and their data types at the beginning of a computer program, like in languages that are strongly typed like C++. So don't assume knowledge of variables that shouldn't be there. You declare your variables, what they are, in the proof. Make it self-contained so they don't have to look for outside references. At a later point in your proof, you may introduce a new variable to represent a quantity that is known at that point to exist. So say you have an integer n is even, and then you know that n equals 2 times some integer, and you give this integer a name so you can work with it concretely later in the proof. Thus, if you decide to call the integer, say, s, you could write, since n is even, n equals 2s for some integer s. All right. Number 4. Write your proof. Write your sentences. In grammatically correct form. This does not mean that you should avoid using symbols and shorthand abbreviations, just that you should incorporate them into sentences. So you can put equations in sentences and still be complete grammatically correct sentences. Keep your reader informed about the status of each statement in your proof. Make status clear. Now, what this means is your reader should never be in doubt about whether something in your proof has been assumed or established or is still to be deduced. If something is assumed, preface it with a word like suppose or assume. If it is still to be shown, preface it with words like we must show that, or in other words, we must show that, so on and so forth. This is especially important if you introduce a variable in rephrasing what you need to show. Give a reason for each line in the proof, each sentence. Give a reason, a step is made. Each assertion in a proof should come directly from the hypothesis of the theorem or follow from the definition of one of the terms in the theorem, or be a result obtained earlier in the theorem or in the proof, or be a mathematical result that has been previously established or is agreed to be assumed. Indicate the reason for each step in your proof using phrases such as by hypothesis or by definition of or by theorem, whatever, and so on. Include little words and phrases that make logic of your arguments clear. Make arguments clear. When writing a mathematical argument, especially a proof, indicate how each sentence is related to the previous one. Does it follow from the previous sentence or from a combination of previous sentence and earlier ones? If so, start the sentence with the word because or since and state the reason why it follows, or write then or thus or so or therefore or consequently. It follows that. Include the reason at the end of the sentence. If a sentence expresses a new thought or fact that does not follow as an immediate consequence of the preceding statement, but it is needed for a later part of the proof, introduce it by writing observe that, or recall that, or now. Sometimes in a proof it is desirable to define a new variable in terms of previous variables. In such a case, introduce the new variable with the word let. Like let n be an integer such that m is 2n. All right, let's see here. Space. So 8. Display equations and equalities. The convention is to display equations and inequalities on separate lines to increase readability, both for other people and for ourselves, so that we can more easily check our work for accuracy. I'm going to put this as 9. It's kind of a separate section in the slides, but develop your own style. Writing proofs is kind of like writing programs. Everybody has their own individual style of writing programs. Two best of friends working on a program together. When they go to write it, they're going to have different programs. You develop your own personal conventions of how you indent or how you name variables, or where you put punctuation marks, spacing, that sort of thing. It's actually quite easy to tell when two people have copied off of each other, because there will be mixed styles within a single program. And so, you can tell, oh, more than one person worked on this when it was supposed to be an individualized project. Proofs are basically the same way. Two people working on a proof, the same proof, will write it different ways. Word choice, sentence structure, that sort of thing, all an individual choice. It's kind of like writing a paper on the internet for a class. The subject is the same, the facts are the same, and all that sort of stuff, but the presentation is going to be different between individual writers. Okay. Our common mistakes. Do not do this stuff. Arguing from examples. Looking at examples is one of the most helpful practices a problem solver can engage in, and is encouraged by all good mathematics teachers. However, it is a mistake to think that a general statement can be proved by showing it to be true for some individual cases. A property referring to a universal statement may be true in many instances without being true in general. The only way you can use arguing from examples is by doing an exhaustive proof, where you take all the elements of the domain and show that the statement is true for all elements of the domain. Now, this is impossible with an infinite set, like, say, integers or rational numbers. But for a finite set, it is possible. But it's just generally easier to write for the general. Use the same letter to mean two different things. Now, say you have m and n as two odd integers. Then by definition of odd, m equals 2k plus 1, and n equals 2k plus 1. That would mean m and n are equal, right? If you have both of them in terms of the same variable, k, so that's a situation where you're using the same variable in two different instances when two different variables is called for. Let's see here, jumping to conclusions. I think we covered this one before. Jumping to conclusions is when you allege the truth of something without giving an adequate reason. Consider the following proof that the sum of any two even integers is even. Suppose that m and n are even integers. By definition of even, m equals 2r and n equals 2s for some integers r and s. Then m plus n equals 2r plus 2s, so m plus n is even. Missing a few steps in there, mathematically. The problem with this proof is that to show an integer is even, one needs to show that it equals twice some integer. This proof jumps to the conclusion that m plus n is even without having found an integer that, when doubled, equals m plus n. Assuming what is to be proved. Assuming what is to be proved, it's a variation of jumping to a conclusion. So suppose m and n are odd integers, then when any odd integers are multiplied, their product is odd. Hence, m times n is odd. Well, you're trying to prove that two odd integers, the product of two odd integers is odd. You're just assuming it to be true and just jumping to the end without showing the intermediate steps. Another one. Confusing what is known and to be shown. A more subtle way to jump to a conclusion occurs when the conclusion is restated using a variable. Here is an example of a proof that the product of any two odd integers is odd. Suppose that m and n are any two odd integers. We must show that m times n is odd. This means that there exists an integer integer s such that m times n equals 2s plus 1. Also, by the definition of odd, there exists an integer a and b such that m equals 2a plus 1 and n equals 2b plus 1. Then m times n equals quantity 2a plus 1 times the quantity 2b plus 1. which equals 2s plus 1. So since s is an integer, m times n is odd by definition of odd. Nah, it doesn't quite work that way. You're just restating the what's to be proved using variables and assuming it to be true. In this example, the author restated the conclusion to be shown as m times n equals 2s plus 1. But we only know that the integer s exists if we know m and n is odd, which is what the author is trying to show. Thus, in the sentence starting with the word then, the author jumped to an unjustified conclusion. Okay, here's one. Use the word any when sum is called for. There are many situations in which the words any and some can be used interchangeably. But for example, suppose n is a particular but arbitrarily chosen odd integer. By the definition of odd, m equals 2a plus 1 for any integer a. Not any integer a, just one particular integer a. So it would be for some integer a. So confusing of the words any and some. Sometimes you can use either one, but I mean, so you could say for any integer, any odd integer m, the definition of odd m would be equal to 2a plus 1 for some integer a. Or you could say for some integer, suppose some particular odd integer m, by definition of odd, m is equal to 2a plus 1 for any integer a. The first sum and any can be used interchangeably. But the second one, it needs to be some integer a instead of any integer a. Another common mistake: misuse of the word if. This is not serious in itself, but it reflects imprecise thinking that sometimes leads to problems later in a proof. This error involves using the word if when the word because is really meant. So, for example, suppose p is a prime number. If p is prime, then p cannot be written as a product of two smaller positive integers. The use of the word if in the second sentence is inappropriate. It suggests that the primeness of p is in doubt. But p is known to be prime because of the first sentence. So you don't use the word p if p is prime. You say because p is prime, it cannot be expressed as the product of two smaller integers. Let's see here. Get a little example here. Prove that the difference of any odd integer and any even integer is odd. Use only the definitions of odd and even and the assumptions that we stated at the beginning of the chapter. And also, but not any other properties of odd and even integers. All right, so first we will state what is to be true, to be proven. For all integers a and b, if a is odd, and b is even, then a minus b is odd. Okay, so we start with stating the what is to be proven. So suppose a is so the proof would be, suppose a is some odd integer. Suppose b is some even integer. And then say, since a is odd, then a equals 2m plus 1 for some integer m. Okay, by the definition of odd. The definition of even could be used to show b is equal to 2n, is equal to 2n b for similar reasons. And then a minus b equals 2m plus 1 minus 2n. So by commutative property, let's see here. that it would equal to 2m minus 2n plus 1, which then would be 2 times m minus n plus 1, distributive law, and then m minus n is an integer, because integers are subtraction is closed on the set of integers. Assumption that we can make according to the rules it gives. So a minus b equals 2k plus 1 is an integer. M minus n is an integer called k. And we'll call it k. And therefore, a minus b equals 2k plus 1, which by the definition of odd means that a minus b is, in fact, an odd number. So that's theorem 4.2.1. Difference of an odd integer and an even integer is odd. Let's see here. Showing that an existential statement is false. Okay. Now, showing a existential statement is false is most practically done by showing that the negation of the statement is in fact true. The negation of an existential statement is a universal statement, right? So to prove an existential statement is false, prove that the corresponding negation universal statement is true. Show that the following statement is false. Let's see, where is that? There's a positive integer n. N such that what is it? N squared plus 3n plus 2, n squared plus 3n plus 2 is prime. Did I write that right? Yeah. Okay. So, proving that the given statement is false is equivalent to proving its negation is true. The negation is so we'll take the negation. It would be for all n element of z plus n squared plus 3. Oops, I wrote that wrong. It's 3n, not 3 to the n. 3n plus 2 is not prime. Okay? So, we'll start with saying n is an element of z plus positive integers. Factoring shows that n squared plus 3n plus 2 equals, what is that, n plus 2 times n plus 1. Yeah. And then you have n plus 1 is an integer, is an element of z plus. N plus 2 is an element of z plus. Because they're the sum of integers, and both n plus 1 is greater than 1 and n plus 2 is greater than 1 because n is greater than or equal to 1. So at minimum n plus 1 is equal to 2. So the product of the two, the product of the two is not prime because it is a product of two integers, each one greater than 1. So for all integers n, doesn't matter what they are, n squared plus 3n plus 2 is not prime. All right. And let's see here, move on to the next section. More about direct proof and counterexample with rational numbers. Rational numbers. Definition of a rational number. There exists R is an element of Q if and only if there exists A, B, element of Z, such that R equals A over B and B does not equal 0. Does that make sense? So R is a rational number if and only if there exists an integers a and b such that r equals a over b and b does not equal 0. So is 10 divided by 3 a rational number? Yeah. 0.281, is that a rational number? 281 over 100, or 1,000. 7, is 7 a rational number? Yeah. Is 2 over 0 a rational number? No, because b has to be not 0. It has to be not 0. It could be less than 0, it just can't be 0. Is 2 over 0 an irrational number? Is it? It's not a real number, so it's not a irrational number. All irrational numbers are real numbers. 2 over 0 is not a real number. Therefore, it's not irrational either. It's in C++, I believe, functions that do division by 0 return not a number, NaN. Let's see here. Let's see here. Oh, one thing that is helpful for dealing with rational numbers is the zero product property. Yeah. Zero product property. If if m n does not equal 0, then m does not equal 0 and n does not equal 0. Does that make sense? To get a product with the result of to get a product of 0, one of the two factors has to be 0. So if the product is not 0, then both of the factors are not 0 as well. It's a handy little property that you will come in handy later in the chapter. Let's see here. Most problems, of course, are going to be stated in informal language, but solving them requires translating them into more formal terms. So let's prove some properties of rational numbers. All right. Prove that the sum of any two rational numbers is rational. All right. So state formally for all R and S element of rational numbers. R plus S is an element of rational numbers as well. Let's see here. So we're gonna say do the proof briefly, and R equals A over B. B does not equal 0. Definition of rational. S equals C over D. D is not equal to 0. And then R plus S equals A over B plus C over D. And then by the multiplying each element to make it a common denominator, this is equal to AD over BD plus BC over BD, which in turn equals AD plus BC over BD. And since because all the A, D, B, and C are all integers, this is the numerator is an integer and the denominator is an integer. Therefore, therefore it's rational. So the sum of two rational numbers is rational. All right, let's see here. Some additional results about even and odd integers. I'm just going to read through them instead of putting them up on the board. Just real quickly here. The sum, product, and difference of any two even integers are even. The sum and difference of any two odd integers are even. The product of two odd integers is odd. The product of any any even integer and any odd integer is even. The sum of any odd integer and any even integer is odd. The difference of any odd integer minus any even integer is odd. The difference of any even integer minus any odd integer is odd. So it has an example to get to go by here. Prove a squared screwing up. All right. Okay. Prove a squared plus b squared plus 1 over 2 is an integer. if A is odd and B is even. Okay? Using these properties. So, therefore, let's see here. A squared is odd because it's a odd number times an odd number is odd. Product of two odd numbers is odd. Therefore, a squared equals 2k plus 1 for some k element of z. And b squared is even because an even number times an even number is even. So that would be, so b squared equals 2j plus 1. J is an element of the integers. So now we have 2k plus 1 plus 2j plus 1 all over 2 by substitution. Consolidating elements, you get 2k plus 2j plus 2 divided by 2. And the 2's cancel out, so you get k plus j plus 1. Right? Yeah. I did something wrong here. No? Oh, okay. And then, so this is oh, well, so this is because it's closed to integers, addition. J and k are both integers. 1 is an integer, so therefore the equation is an integer. It's not a rational number in that with a denominator of 2. It is a whole number. All right. All right. Well, do we have time to do how many? How many slides we got? I think we can call it a day at this, and we'll save divisibility for next Tuesday.